Welcome back to math class, everyone. Should be machine learning, and hopefully it's going to be machine learning soon, but for now it's still math. And I think today we'll actually get to the supervised learning problem and defining some more exciting things about it. But for now, we need to finish probability, and that's what we do first. And I have a few little comments about what we've discussed so far, maybe some like things I've noticed that people had some confusions about. Yeah, so mainly it's this outcome versus event thing. There's some confusion about like what is the difference, because maybe in like English language, sometimes you would refer to an outcome of an experiment or like an event of the experiment maybe as like the same kind of thing. But the important thing is that when we work with probability stuff, there's like a formal difference between the two. And okay, so the high level story is there's something called the outcome space, and I'll just like write it here. For instance, for the roll of the dice, right, this was the outcome space. Inside the outcome space, you have outcomes. When you do the experiment, you get an outcome, which means you get something like, let's say you get an outcome, and maybe it's 3. So your outcome is 3. You could roll the 3. You always, from like when you do your experiment, you always get an outcome. And that's usually represented as like a random variable. You would say something like your random variable x, which maybe I'll write here. You would say x like belongs to this outcome space. And then you would say something like x equals 3. That means your outcome is 3. The random thing, the random outcome is 3. Random variable is 3. This is all kind of the same thing. Okay. But then you might want to ask, like, talk about things other than just getting like a single outcome. You might want to ask, like, what, like, you might be interested in what's the chances I get something larger than 4, let's say. You would call this like kind of question an event. So that event of getting something larger than 4 would be written as a set. And the set would be all the values that mean this like English sentence larger than 4. And that'd be like 4, 5, and 6. Okay, so event is kind of like this like property you care about that your outcomes would have. Okay, and so then you would read something like this as not the probability of getting the numbers 4, 5, and 6 all at the same time, but as the probability of your outcome, which is just a single number, such as this, being one of these numbers in your event. And so we have this like shorthand notation that's usually written, but this is how it's always written, is like that your random variable, you should think of it as like your random outcome from your experiment, is one of the elements in the event. And so it's written like this. So once again, this would just be saying like, what is the probability that rolling a dice would generate an outcome x, being 4, 5, or 6, being a number larger than 4. So clearly there's a distinction between these like events, which are sets containing outcomes, and outcomes, which are just single numbers from your outcome space. So this is like sort of maybe like you might think it's simple at face value, but when you start working with it, you'll quickly see there's like an important distinction between these two things you should always remember. Because once again, these probability distributions take as input events, and these PMFs and PDFs take in as input outcomes. Okay. And then there was just another note I wanted to make, which is that in the like these course notes, I made a slight correction, which is in this marginal distributions, there is a slight typo. And I'll just mention that when I go through it in a second here. Okay. So I'll spend like the first 5 minutes just giving like a high level overview of what we did so far and then what's coming up in this class. Okay, so there's this whole, like we're doing probability, so we care about the probability of some event happening. I've already described what this event is. And formally, the probability of something is like denoted by this distribution function P. Okay, so let's get to there. So there was this probability distribution. This describes the probability of an event. Okay. Then I told you there's these two other functions called PDFs and PMFs. And you should think of them as just like helper functions to calculate this probability distribution that you really care about. And the important formulas here were the following. This is the formula you use if you have a discrete random variable and you want to calculate the probability of some event. This is the probability of some event. What you do is you use this PMF function, little p. If it's a discrete random variable, use this. This is like the thing to know. You want some probability, use this. If in the other case, the random variable is continuous, right? So your random, oh, sorry. Oh, this is slightly wrong, but okay. This should have said uncountable. Let me fix this. uncountable. Right. So if you want to talk about continuous random variables, then you use these probability density functions. Okay. And this we use a little p as well, but here when it's a probability density function, it's different than a PMF, and we use integrals. But the point is if you have a continuous random variable, you use this PDF to calculate the probability of an event. This is going to be like the kind of like the most important story of all this probability stuff. Every time you kind of are asked to calculate any probability, your first instinct should be, okay, is it a continuous or a discrete random variable? And then once I know that, what is the corresponding PMF or PDF I should use? Because that's the thing that's going to actually allow me to calculate things. Okay, so then that's really the trend that ends up happening for the rest of the things we talked about. So after that, we talked about not just distribution or like the probability of a single random variable, of a single kind of like outcome. We talked about these multivariate random variables, which you can think about as the probability of multiple different kind of like outcome spaces or like experiments. And so one example was here you could talk about the probability of like flipping two different coins. So you think about the first coin is one experiment, the second coin is another. So you'd write a new random variable x, and you would have two random variables, one being like the first coin, the second being the second coin. The story here ends up being basically the same as before in terms of how we calculate things. And what I mean by that is that you just calculate things by using like the PMF or PDF. And I didn't even write the definition down because it's exactly the same as before. So like in this example, if you want to calculate the probability of some event, you just use the PMF because here is a discrete random variable. So story is the same. Okay. But once we have these multivariate random variables, there's more interesting questions that we can ask than in the single like variate case. And what I mean by more interesting questions is I mean we can ask about these things called marginal distributions, which is just like what's the probability of like a single random variable, excluding all the others. Forget about, we don't care about the other, just one single variable being something, and that's called like this marginal distribution. And then there was formulas for this as well. How do you calculate this? And once again, what do? You use the PMF or the PDF. Okay. So what I mean by that is if you have a discrete random variable, you have a formula like this. It's exactly the same as what we've seen before, except now we have a marginal PMF, right? Before we had this like PMF for a single variable. Now we have this thing called a marginal PMF. It's still a PMF for a single variable, except now the way you actually get it or calculate it is through kind of, well, you sum up the values of all other variables except for the one you care about. So this was where the minor typo was. Before, this was not written like correctly. It was something else. Whatever. The important thing is that this thing takes as input all of all the different outcomes that could be there, and the sum is over everything other than the xi value. So the important thing is that here, like in somewhere in there is xi, and that's the only thing you're not summing over. So you sum over everything except for xi. So what you get left with is just a function of xi, which is what this is. Anyways, moral of the story is you want to calculate the marginal distribution, you use the marginal PMF. If the thing's continuous, and what I mean by the thing, I mean the random variable, if it's continuous, then what do you use? You use the marginal PDF. Okay. And then there's examples going over how we get these things from the original joint PMF or PDF and stuff, but this is like always the story is you kind of need this like marginal thing to calculate, you need the PMF or the PDF to calculate the distributions. Okay. That was this marginal thing. And then there was one more thing, one more kind of like probability distribution you might be interested in for multivariate random variables. And that is this idea of a conditional distribution. So now that we have like multiple variables, you might say like, what's the probability of one variable conditioned on the others? Okay. And this is in contrast to the marginal. The marginal one doesn't care about the others. Just says, what's the probability of this random variable being this? I don't care about the others. Conditional means I want the probability of this random variable, but given some, like the other variables are equal to something else. Okay. And then there you also have, once again, similar story. This is how you calculate things. You have a PMF or a PDF. This time it's called the conditional PMF or PDF. And there's a formula to get it, just like in the marginal case. Here it's this like division formula. That's the moral of the story. Yeah, continuous case, you have a PDF, so you use integrals. That was like the kind of when you're actually solving these problems, this is the thing you want to remember. Then you like use these formulas and stuff. Okay. Then there was some examples. I'm not going to go over all those. maybe one of the last thing I should mention here is when you have these multiple random variables, there's also this notion of independence, which you would kind of think of like one experiment is independent of the other, meaning like one random variable is independent of the other. And formally, what that means is that the PMF or PDF can be written in this product form. So that means it can be written as just the marginal of x multiplied by the marginal of y. Or maybe the more intuitive way to think about it is that the conditional PMF or PDF is equal to the marginal. So, and what that means is like the probability, like you can think of, for PMF case at least, you can think of these as kind of representing the probabilities. And here you would say like the probability of x given y is the same as the probability of x. So it doesn't matter what y is, x doesn't depend on that. So, and the example I gave is like 2 coin flips. If you flip a coin and then you flip another coin, then the second coin flip should not influence what your first coin flip is. It doesn't matter if the second one was heads, if the second one was tails, doesn't say anything about the first one. So that's a case of independence. In general, when you have more complicated things, it's not so easy to just intuitively think about it. And what you have to do is you work out the formula and see if either this or this property holds. If it does, then it's independent. If it doesn't, it's not independent. And unsurprisingly, you're going to work through this in the next assignment for a bunch of different cases. Okay, that was the story. And then there was this brief discussion about like, well, what if your multivariate random variable, what if like y is discrete and x is continuous? We technically haven't covered it, and we are going to talk about it in the tutorial today, so I'm not going to go over this today. And then we ended off with this part, which is talking about how our data set can be just thought of as a multivariate random variable. Okay. And I'm briefly going to discuss this too. Oh, sorry for not putting it on the full screen like this. Yeah, so this is the data set represented as D. We think of it as a multivariate random variable containing n random variables. Each of these random variables represents like what we call a feature label pair, or you could think of it as like a data point. One simple example is this represents the flip of a coin. This is not like a machine learning example, but like a classic probability example. So you'll think of this as n coin flips. Okay. And then turns out in the machine learning world, these things are more complicated than coin flips, but nonetheless, they're random variables, Zi, and they themselves are multivariate random variables. They are the random variables x and y, and x represents the feature, y represents the label. Okay, and then story goes the same as what we've seen for multivariate random variables, like this big complicated D thing has its own distribution. That's the distribution of D, it's just the multivariate distribution. Each one of these individual feature label pairs has a distribution that's called P of Zy. It's the marginal distribution. Okay. And the important property we're going to assume in supervised learning is that each one of these feature label pairs, which is like these random variables representing feature label pairs, are independent. And this should be like, this is actually the exact same case as with a coin flip. Each coin flip is independent of the other. Doesn't matter what I got in the first coin flip, the other doesn't matter. In the feature label pair case, like, doesn't matter what house and price I saw here, I'm going to go gather a random house and price again, or someone's going to give it to me. Like, it's not going to depend on the previous one. Okay, that's the assumption. The other one is that all of these random variables, which let's do the coin flip example, come from the same distribution, which is this P of Z. Okay. And what that means is that, like, for a coin flip, that would mean every single coin is a fair coin that you're flipping. You flip n coins, all of them are fair coins. So they all come from the same distribution of a fair coin. If instead, let's say like the second coin you flip was an unfair coin, then you would not say that all the coin flips are coming from the same distribution. You would say like, oh, maybe the second coin flip comes from this other like P of Z2. This thing is actually different than the others. That would be an example of not being the same distribution. And in this case, we're just saying you're gathering like houses and their prices from, let's say, like some city, and all of them are coming from the same city. That's like the distribution you're coming from. If you instead gathered a house and a price from like some other city, then that would come from like a different distribution. It's the probability distribution from that other city of houses and prices. Okay. So this is the assumption. We're gathering all the data from, like, let's say the same city of house prices, and all of them are independent of the others. And formally, that just meant that the distribution over the whole data can be written as a product, meaning these are all multiplied by each other, and they all are the same distribution. Okay. That is like the implication of all this assumption. And yeah, and like intuitively in words, you should really think of this as saying that the data set D contains n independent samples of these feature label pairs, and they all come from the same distribution. Okay. And there was one quick question, which was like, if you're ready, oh, sorry, does P of X comma Y mean in the definition of independence? Oh, I assume they're talking about this, and we can quickly go over that. So in the definition of independence, which is here, this thing is either a PMF or a PDF, depending on your random variable. And so independence means that the PMF or the PDF can be written as this product. But in general, this also holds for distribution. So if you write something like this is the thing we actually saw with the data sets. So if you have the probability of two different events, like this random variable being this or this other random variable being this could be like your first coin flip being heads, and then maybe your second coin flip being heads or tails. Then you can factor it into these two things, which would be like the probability of the first coin flip multiplied by the probability of the other. This should be kind of intuitive. Like the probability of getting heads on the first coin flip and tails on the second is just the probability of getting heads on the first one multiplied by the probability of tails on the second. That would just be 1/2 times 1/2 equals 1/4. That's what it really means. Okay. And so now we move on to the new stuff. Why is P of Z written as the product? I don't know where P of Z is. Oh, this one. Yeah, so it's written as a product because this thing is a multivariate distribution. What does it mean? It means it's a distribution over multiple variables, the variables being Z1 to Zn. And since it's independent, I can just write it as the product of the distribution for each variable. This is the distribution of the first variable, and then I write it as the product. There's n of these here, all up to the last one. That's why that happened. Okay. Moving on. So this stuff is going to be, again, just a little bit of probability, and then I mentioned at the end of this about how this is related to supervised learning again. Okay. So there's going to be a very important concept, and this sometimes isn't maybe exaggerated as much as I'm going to exaggerate here, but I think it's just super important to know this. So pay attention. This idea of functions of random variables are still random variables. Yeah, that's like, if you remember anything about this thing right now, is that if you have a random variable and you apply some function to it, so if you have x and you apply the function x squared, so you get a new thing called the random variable squared. That thing is still a random variable. And this is true for any complicated function you're going to apply to any of your random variables in this course. They're always still going to be random variables. So let's go over an example. So imagine you have this like x being a fair six-sided die, the case we've been doing already a bunch in this class. We would normally write we have this random variable x. It belongs to this outcome space. I just written this shorthand for the outcome space. And this is the PMF. It basically tells you that the probability, like, yeah, it's a uniform probability. Each outcome is equally likely with 1/6 probability. Okay, so here's the interesting thing now. Now we have a function, f. What is that function? That function is the squared function. So we take in x and we square it. I already said this is a random variable. This is like the real important thing to take back. If you apply a function to a random variable, you get a random variable back. Okay, what does the outcome space become? It becomes the original outcome space with every single like possible values, like with the function applied to it. So here that would mean you take the first value 1, you square it. You take the second one, square it. This is as you would expect, right? You have like what I mean, it's like you have a function. It takes in as input this calligraphic x, which is the original outcome space. What does it do? It maps to a new space y. And that y, which we call the codomain, and in this case is actually exactly the range. I've made them equal. This y is just going to be exactly what does the function map each possible input to. Okay, so that's the new outcome space. It's not usually going to be that important to know what this new outcome space is, but this is what it is. The point. Okay. So sometimes you're going to see this thing too, and this might be a little bit confusing, which is that you apply this function, and this is how you think of writing it, and this makes it like very intuitive what happened. You applied a function to a random variable, And just like with any normal variable, when you apply a function, you just write it like this. People like to write new symbols to represent these functions, such as like y. You would say like, oh, we have a new random variable y, and maybe this is to indicate that this thing is actually a random variable. And then you would say like, oh, y equals to x squared. This y and this f of x, they're the exact same object. They're both random variables, and same with like x squared. These are all the same thing. They're all random variables. Okay. And I wanted to point out one more thing, which is that, okay, so yeah, in this case, there's this like interesting property that there's going to be a PMF for y as well, right? Y is a random variable. So it of course, it has its own PMF because it's discrete in this case. In this case, that PMF ends up being that the probability of any one of these values y intuitively is like the same thing as before. It's still 1/6. Okay. So what I mean to exaggerate in this case is it turns out that like the probability of the squared version, x squared, is the same as the original version, which would be like just x. So they're all 1/6. This is not always the case. And we're going to see in the next example, this is not like the case and it's more complicated and stuff. But what I wanted to say, like really communicate, is that the random variable is this x squared thing. But the PMF thing in general, like there's going to be a complicated story about how you get this PMF for this function y, or this new random variable y. And it's not just going to be as simple as take the old PMF or like square the old PMF's values or something. And here's the example like pointing this out. And I have it in red in a second to really make it clear. So you might think of another example, which is like, suppose this random variable x represents payouts from a slot machine. And what that means is you play a slot machine, you either like the money you pay for it and then the money you win back, that's called your payout, let's say, and you either get like some value between -10 or 10 from the slot machine. Like if the casino's doing a good job, on average, you should be getting something that's negative probably. Okay. An example of a PDF in this case might be this uniform PDF assigning a density of 1/20. This means a uniform density over all the possible outcomes. This is probably not the case in like a casino, but this is the simplified case. Okay. Then we have this random variable again, just x squared. So same exact random variable. We can do this, of course. Now the outcome space becomes bigger, or it becomes different, sorry. It becomes all of these values, like the corresponding, what does the function map it to? It maps it to values between 0 to 100, right? Because -10 gets mapped to like 100, -10 squared, I mean. Okay. Here's the interesting thing, is that there is, of course, a PDF for y. This turns out to be the PDF, and we're not going to talk about how to calculate it in this course. The point of the story is that there's going to be some PDF for y, which describes kind of how is the density distributed over this new random variable x squared. It becomes this thing. This is quite different from this. Like there's a y in here. It's depending on y. This thing is uniform. It doesn't depend on x at all. So the story is it's much more complicated. And in general, this is the case. In general, if you apply a function to your random variable, the corresponding probability density or probability mass function is not just the random variable squared. Notice it's not just like 1/20 squared or something. It becomes a complicated story. That's the thing that I really want you to understand. So like, we're not going to talk about how to get this thing, but we should understand is it's not just p of like the original thing squared or function applied or anything. Okay. But it turns out that for the purpose of this course, there's going to be like a thing we're going to see in a second about how to like avoid needing to know this complicated PDF to do any calculations and so on. But I just want you to kind of understand this thing. Yeah. Okay. But the main takeaway is that random variables, if you apply functions to them, they're still random variables. And yeah. Okay, why am I emphasizing this? Well, it's like it's immediate, right? Remember in this course we had this data set. It was a random variable, right? And then there was just two functions we cared about, which are the learning function, like the learner. I called this learner a function, and there's a predictor. That's also a function. Well, no surprise here. These things are going to be functions of random variables. And so no surprise is that, as I just said, functions of random variables, they're still going to be random variables. So let's go over what I mean. So let's do the predictor first. The predictor was this. Let's see what it is. So first of all, the predictor was something like this. It was a function that mapped from x, which we thought of as our features, to y, which was our labels. We might think of the features as being like some vector in the space R2, maybe representing the number of rooms and like the age of a house, let's say. So what does this function do? It takes in this information about a house, that's this thing, and then it maps it to some value y, which is like the price. And so here y would be like a real number as well. A simple like example of this function is, let's say you take in this x thing, which is written as x1, x2, and then maybe you decide that you're going to multiply the number of rooms by 6, and then multiply the age by this, and then add 3, and then you get the price of the house in hundreds of thousands or something. I don't know. Who knows why you chose this predictor, but let's just suppose you chose this predictor or something. The point of the story is that if it takes as input a random variable, this whole thing is still a random variable. Now it's a more complicated function, maybe than x squared too. But the point is that this is a random variable. And what's its outcome space? Its outcome space is y, which is just the real numbers. Okay. And it has a corresponding distribution. We're probably not going to talk about that often, but like you should know that this is the distribution of this random variable, which is the predictor applied on this random feature. Okay, so we will call, like, sometimes I'll call the features random features, like, and you should think of like, this is the information about a house, which you're randomly getting from like someone's gathered this data. This is like random information that was gathered. Okay, so takeaway from this is the predictor, when passed in with like some random feature, you get some, it's still a random variable. Okay, I'll explain the importance of this after just mentioning the learner part now. Okay, so there's another function we had, which is a learner. This seemed more complicated, but let's just go through the notation again. So just for the meantime, think of D as a random, okay, not for the meantime, it is a random variable, but forget about, it has, okay, this is the complicated form it has, but it has some form. It's a random variable, right? And if we apply a function, which is called the learner function, A, to this random variable D, which is our data set, we get a function as the output. That was the definition of this learner, right? This learner took in a data set. This is the set of all data sets, and it outputted something in this set, which is a function. Okay, so it takes in data set, outputs function. And since the data set is random, and I apply a function on something random, what do I get back? I get something random. I get a random variable. And here, this might feel a little weird or complicated and stuff, but the random variable is now a function. Okay, which is still fine. Like I said, you can use random variables to represent anything, not just numbers and stuff. So now, that's okay. What is this outcome space? This outcome space is the space. So this is like, this random variable takes values in the outcome space, this calligraphic f. And this is just a set, right? This is the set of all functions. You've been used to like seeing sets of like numbers 1, 2, 3, 4, 5, 6. Now you can have functions. And you can imagine like one example of a small set of functions would maybe like x squared, x cubed, x to the 4. Maybe this is your set. Still fine. So everything like intuitively should apply. The math, you can see, starts becoming more complicated, and like we're not actually need to work through a lot of this math with these complicated functions much of the time, but we're going to need to say things like, what is the expected value of like the predictor, the function we get here? Like, what is the expected function we end up outputting? And saying these kind of terms are meaningless unless you understand the fact that, oh, this thing is just a function of a random variable, so it outputs a random variable itself. Or sorry, this thing is a random variable, and you can talk about these things. Okay. And let me just mention this point in purple here, which is the importance of all this is that we're going to be able to talk about things like the following, which is like, what is the probability that our predictor, right, which is the thing that's supposed to predict house prices, outputs some value y, right? So we can ask like, what is the probability that we predict some value y, right? So if we get like some new house, we might ask like, what is the chances it predicts the correct price? And this is all meaningful now because we just think of this predictor, it's like, it's just a random variable. It does some operation on the original random features, and it gives us a new random variable, which is the price. Clearly, if the features change, that's the random part, then the output price also changes. So you might want to know, like, what is the probability you get some price? Okay. And similarly, this is where things might seem a little more complicated, is that the learner itself is outputting a different type of predictor depending on the data set. So if you get like, for instance, like, let's say 10 houses of some type, imagine they're all like really expensive houses for some reason. Well, then you might, like whatever process you use to produce your predictor, but you might produce a predictor that like thinks houses are really expensive. Well, if your data set was different, like you got some new different data set, which was all the cheap houses for some reason, that's what you end up being given, then you might produce a predictor that thinks that houses are cheap. Okay? So like the point of the story is we might want to ask, like, what is the probability that this learner outputs some predictor that predicts house prices that has that like predicts cheap house prices or more expensive ones and things like this. And maybe just to like tie this back to this whole ChatGPT thing, you would think of this as like ChatGPT is like what's the data it gathers? It gathers, okay, so there's some algorithm that does the learning and it produces a predictor called ChatGPT. And you might want to ask, like, how, like, what is ChatGPT going to be good on? Like, what is this ChatGPT thing going to look like? Well, it's going to depend on the data I gathered. So if it gathered data that like was only math from math textbooks, then maybe this learning algorithm, which is like complicated, like gradient descent stuff, whatever, it produces ChatGPT. Well, if the data set was different, then maybe ChatGPT would know different things. And so like, yeah, so if you change the data set, the corresponding predictor might change. And you could imagine people like at like these companies might care like what kind of data set do I need to produce a predictor that is of like some quality? Like, what's the probability that I get a predictor that knows math and science and everything well? Well, that's going to depend on this random variable called the data set. It's going to depend on the data set I'm given. Okay, so this is my whole long story about why these things are important. And we're soon going to talk about these, like, we're going to need to talk about things like that. Okay. And there's two questions. And the question is, why did x squared become this interval? If I wrote equals to, then that is not good. Okay, it did not write equals to. So I wrote this, which just said that x squared, right? It means that the values that x squared can be are in this set. It means that they can be values of 0 up to 100, which should make sense, right? What is x squared? It takes values from this set and it squares them. So if you had, like, for instance, the value of -10, it would be 100. That belongs to this set. If you got like the value of -3, what value would it be? X squared? X squared would be 9. That still belongs to this set. So this is just the set that this random variable belongs to. It's like the same thing as the range, basically. And it also says in the learner, if the D is a huge tuple, how will we write the FD? Okay, so let's just go over the example I had here, which I didn't explain. But like, we're going to talk about, this is going to be like basically the discussion of the whole course. I've said a few times and it's coming up, is that we're going to talk about what does it mean to take a data set and produce a predictor. And like one really simple example, which we won't actually be doing, but like, because this is like very naive and not good. But imagine your data set is like this. So you have 2 houses in your data set. And what that means is like, maybe you have a house with 7 rooms and it's, let's say, $600,000. That's what 6 means here. Maybe it has 12 rooms. Okay, and this is a bad example. It's 250,000. I don't know, for some reason. Well, then what do? You need to produce a predictor function, which means you produce a function that takes as input some x, which is going to be like the feature of a new house, maybe the number of rooms of a new house, and produces a price. But you can use the data you've seen, or you don't, or whatever, but you have access to that data. And one way to use it in some silly way is like, I don't know, take the second house and put its price as like the constant. So for some reason, you think that's the number there, and then take the price of the first house and put it as the multiple of this new house you see. And for some reason, you choose this to be your function. It's not going to be what we learn, because that would be more complicated to write here. But the point is, this is like a simple example of how you can use D as input, right? D is the input to here, to the learner. And what do? You output an F. And the F made use of the D, and now this F can predict new house prices. You pass in an X, which is like a new house, the information of a new house, the feature of a new house. You predict the price of the new house. Yeah, so we'll be talking a lot about this very soon. Yeah, there's a question.
So what would be distribution of like a function of like this when we were talking about this stuff before, we were talking about numbers, right?
Mm-hmm.
So that's like you can imagine that, but well, how would you draw the distribution of different functions?
Yeah, so that becomes much more complicated, and we're not going to like talk about PMFs over functions and stuff. But like, once again, maybe like a really simple case is, imagine this F, for instance, was not equal to, but like it was a subset of all functions. And for instance, maybe this F was just the function, like the set of functions, which was only like x squared, x cubed. Maybe these are the only functions you decide to output for some reason. Well, then like you could draw the probability distribution of this, maybe, and it would be something like, well, you just plot like what's the probability of getting each one of these functions, and that would be it. But like obviously there's way more function than this, and it's much more complicated story, and maybe they're all equally likely. So maybe you have a 1/3 chance, but you could it's like a really simplified version of this, yeah. And this would be like the probability distribution of the random variable, which is, well, in this case, we'll have like maybe this guy. Okay, so this A of D is the learner. It takes values that are functions. They're in this class, this set of functions. And each of them have a probability of being like output. Maybe that probability is 1/3 in here, because you can only output 3 functions. And this is like, here I outputted a function that's not in this function class up here. But anyways, yeah, this is like a simplified thing. But you should think about like, in general, there's like all these functions. There's going to be like, what we're actually going to consider is all possible linear functions, which means like all the functions of the form, let's say a, or what is it called, mx plus b usually. And now m can be any number and b can be any value. So that's like an infinite class of functions. And then you have a distribution over this like uncountable space. And this is kind of where this continuous random variable stuff comes in. But the point is you kind of like can think of like, there's going to be some distribution over these functions. And you want it to focus more on the functions that are good functions for predicting house prices. That's going to be like the purpose. And we're going to talk about like, what does it mean to focus more on this? What we're going to say is like, we're going to want kind of like the expected value. We need like the expected predictor we learn to be a good predictor, to be like the correct predictor. And so that's exactly what we're talking about next, which is the expected values and variance of a random variable. Yeah, okay. Shall we start with that? Okay, so moving away from the data set stuff and the predictor stuff, just think of normal random variables like rolling a dice, coin flips and stuff again. There's this notion of an expected value. And sometimes this can also be messed up by confused with other terms, such as mode or median. Okay, there's like mean, median, and mode. Expected value is the mean. Okay. So here's the intuition. You should think of this as being the average value of some random variable, like the average outcome you see, if you sample from that random variable, if you flip a coin infinitely often. Okay. And just like high level, let me just mention what's coming up. It's like, if you flip a coin infinitely often, what is the average value you're going to see? If you represent tails as 0 and heads as 1, well, the average value is going to be 1.5. But that is not something you actually, like, that's not a coin flip. You can't see, like 1.5 is not even one of the outcomes. So there's already like some weirdness to this, right? So, okay. So there's 2 things to note with this, which is, first of all, if we're going to want to talk about these expected values, we're going to need to like add things together and divide by how many flips and stuff we have, whatever. This is going to require things to be numbers. So we're always going to need, like when we work with expected value, everything needs to be a real number. Because you can't like take the average of a cat and a dog. We're not going to know what that means. Okay. So this is where this like notion of things being numbers actually becomes important. And the other thing is that you should note that the expected value is not always a value we expect to see the most frequently. Okay, that is called the mode, what you expect to see the most frequently. The expected value is the thing you expect to see on average. So if you flip like an unfair coin, maybe like 70% chance of getting heads, the thing you expect to see most frequently is heads. However, the expected value would actually be 70 or like 0.7. Okay, so we'll see this in a second. And the formula for this is, yeah, it's the following. It's going to use these PMFs, and it's kind of intuitive. So we write this notation for expected value, this like double bar E thing. And we say it's the expected value of X. That's how you read this. And the calculation is probably quite intuitive for the version of X being discrete, and something you've probably seen before is that you take every value of X. So this sum says take every value of X, right? And what do? You multiply by this corresponding probability of X. So in the coin flip example, we'll go over it in a sec. But in that case, you would take like 0 and you would multiply by the corresponding probability. Well, that's 1/2. Plus 1 times the corresponding probability, 1/2. Turns out that equals 1/2. That should kind of make sense. Another way to think about it is, like, if you think of this as every outcome, it gets weighted by the probability of seeing that outcome. And then the corresponding thing is the expected outcome you see. Okay. When x is continuous, we say this, like we do the exact same formula, but now we use an integral because there's infinitely many things. We can't take their sum. We need to take this integral, which is like the extension of a sum to infinite things. Okay. That's the formula. Here's an example. For instance, for the fair six-sided dice, what is the average value? Like you intuitively can probably imagine it's going to be like the thing in the middle between 1 and 6. Well, that's 3.5. Mathematically, you take this formula, you take the first outcome, you multiply by its probability of 1/6. Second outcome of 2, multiply by 1/6. Anyways, you write out the whole thing, you get 3.5. That is your expected dice roll. Well, what the heck does that mean? It's not even a number you can roll. You can't roll 3.5. But it's like, as I said, this is like the average value you're going to get. So this is important. It's not always something you can actually roll on the dice. Okay. Same thing with the unfair coin. An unfair coin is usually described by this thing called the Bernoulli, which we've seen before. All that this alpha means is it's just the probability of getting a heads. You write out this formula, as we talked about, and it's, as I said, like 0 times the probability of getting tails plus 1 times the probability of getting heads. What do you get? You get alpha. Okay. Once again, this is not a result of a coin flip. Coin flips we call either getting 0 or 1. Here you get alpha. And unless alpha is 1 or 0, it's not the thing. Okay. That's what you need to know about expected values. Oh, and the other thing is there's this really common probability distribution called this normal distribution. This will come up in the course and in life and in general. It has this really complicated PDF here. To calculate the expected value, oh, you plug in this like terrible integral, and then you have to evaluate this thing, and it doesn't even have a closed form solution. Like, oh, like okay, it actually does, but like the calculation is very annoying and so on. But guess what? It equals to mu, which is exactly the parameter here. And so this parameter, as I said, represents the expected value of the mean. I said this kind of earlier, but so you don't need to know the steps to go from here to here. But what you should know is that the expected value of a normal distribution is this mu parameter. And so visually, what that would look like is it's exactly like, it turns out to align exactly with this peak of each of these 3 normal distributions that we've seen. So that's like one intuition. You should draw what the expected value means in terms of like visually for these normal. And one other thing to remember is that, I should really point out, this is the PDF. Okay, so for normal distributions, the thing I'm plotting here is the density function. This is not the distribution. This is the density of the normal distribution. Okay, this tells you how much probability is in a certain region. So there's a lot of probability in this region, which is the region close to the expected value. Okay? And the way to actually get the probability is you integrate. You get the area under the curve. So this would be like the probability of this region would be this area under the curve. That's where the integral of the PDF is what it stands for. Okay. So carrying on with expected values. As I said, functions of random variables are random variables. I just talked about taking expected values of random variables. Well, we can obviously take the expected value of a function of a random variable. It's just the expected value of the random variable that the function produces. And everything is the same. So the expected value of a function of a random variable is exactly as before. You treat this thing as their new random variable. You plug it in the exact same way as before. Everything is literally identical. Okay. And so for that reason, we can do like one more example. Imagine you have this like payout from a slot machine. If you wanted the expected value of x, we already like talked about how you would get that. You would just use the formula. Well, now imagine we have a new random variable, which is a function of the old one, which is like x squared. Well, you could ask, what's the expected value of x squared? Which I don't know what this would really represent. For some reason, maybe you like someone takes your payout from the slot machine and squares it and then gives you that money. That would be a very unfortunate situation for the other person, but that's what this might kind of describe. And so you can calculate this by, okay, and here's the important part of the formula that I should mention, is that notice what PMF or PDF you're using here. You're using the PMF or the PDF for the random variable x. You are not using the PMF and the PDF for the random variable f of x. Okay? So once again, what you're plugging in here is outcomes of x. You're not plugging in outcomes that this thing maps to. So let me exaggerate here. So like in this case of the slot machine, the PMF of x is the following, 1/20. Okay. The outcome space of x is this. The outcome space for y, which is x squared, is not minus 10 to 10. The outcome space for y is 0 to 100. Okay. So now we look at what does this expected value actually look like. What it looks like is I take this random, this function of the random variable, f, and I multiply it by the PMF of x. Notice here x is going to take values from minus 10 to 10. That's what this thing indicates. Okay. So this is how I calculate this expected value. Okay. And this is why you usually don't need this P of y thing. You can just talk about the original PMF and just talk about integrating over this x value. Okay. There is an alternative though. And the alternative is to actually use it. And what would that look like? And I'll go over this briefly in the tutorial as well. But like you're never going to use this and stuff. But like just for those curious, like you might think like, okay, like if I just represent f of x as the random variable y, like I just wrote y, then I can map the formula one-to-one to what I saw before for random variables, and I would get something like this. And I would actually integrate over the space y, and then I would use the values of y, and here I would use the corresponding PMF or PDF for y. And it turns out you're going to get the same number. These are equivalent, but okay. The point of the story is you're not going to use that formula. You're going to use this formula, which is you use the PMF or the PDF for x, and you multiply it by the corresponding function of x. And once again, what does it give you? It gives you the expected value of this function for the random variable x. So like over this space with corresponding PMF or PDF this. And here, okay, like just in the example, what did we get? We got 33.33, which means like the average amount of money you get back from somebody taking your payout, which is a number between minus 10 and 10, and squaring it and giving it to you is going to be 33. That like somewhat makes sense maybe, right? Because like the possible values you can get is 0 to 100. They're squaring your values, and so you get 33. Okay, so this is the expected values. Probably quite an intuitive concept, but like mathematically, this is what it looks like. So there's another, I would argue, sort of intuitive concept of things, which is the variance. And this word almost describes exactly what it means as well. Like the English interpretation, which is like, you can think of the variance as how much does your random variable vary from its expected value. Okay. So here's the formula. I'm going to give you the formula first, which is that if you have a random variable x, then its variance, written like this, the variance of x, is just an expected value of a function. Okay. This is the function. It's this complicated looking thing maybe, but we can interpret it as, again, like by looking at it. So what is this function? It says take the expected value of x and compare it to the random variable x. So take their difference. And since this thing could be like positive or negative, we don't really want to distinguish between the two. You could take the absolute value, but mathematically it turns out to be kind of annoying. So what people do is they just square it so that it's always a positive number. So like if you vary in the negative direction a lot, or if you vary in the positive direction a lot, if you square it, you get some positive number. So it gives you that mean. So once again, if x is far from its expected value, then this thing becomes large. And so then you have the expected value of something like a large function. Okay. Turns out there's also this useful expression that if you just expand this squared thing and do some manipulation using some properties, I'll mention at the end, you get this thing. This thing will also be useful for calculations. I'm just giving it to you. You will probably need to make use of it. Okay. So that's the way you think of this variance. And I'm going to skip the fair coin one and just go straight to the normal distribution because this will be much more intuitive version of what variance is. So once again, normal distribution has this complicated PDF. If you wanted to explicitly calculate the expectation, as we have already talked about, that was this thing we talked about earlier. Turns out it just becomes mu. If you want to calculate the variance, I didn't even write out what the formula would look like, but you could imagine that thing would look like you plug in this, like, you have to use this function, then you multiply it by the PDF. We're working it out. That takes a long time. But one of the story is it just becomes sigma squared. And so notice how these are the two parameters of your normal distribution, mu and sigma squared. So mu is the mean, sigma squared is the variance. And now we can reinterpret this plot I drew earlier, which I talked about sigma squared. What did it mean? And here, now it should make even more sense, which is that here's three normal distributions. The black one kind of has like let's say like an in-between sigma squared, an in-between variance. The green one has a big sigma squared. That's the variance. It has a big variance. What does variance kind of mean? It means it varies a lot from the mean. Well, look at the plot. This is what like varying a lot from the mean is. It means there's a lot of density, and you can interpret like when you take the area under here, this is the probability, but like to be entirely correct, when I talk about this, this is called, you have a lot of density away from the mean. So there's a lot of variance from the mean. And if the variance is small, then what happens? Then you don't have as much density, which gives you the probability again, away from the mean. So it varies less. Okay. This is so like, once again, low variance would mean that your expected value, or sorry, your random variable, the expected value of the random variable is close to its actual expected value. And that's once again described by this formula. The random variable is close to its expected value in expectation. It's a little confusing, but yeah. Okay. So low variance means you're close to the expected value. High variance means the random variable is like varies farther away. So usually if the expected value is the thing you want, so like let's say the expected value of some function is the actual true price of the house, what you would like is for your predictions of the price to not vary much. So ideally what you would have is like a predictor that has expected value exactly the true price of the house and has zero variance. Like it doesn't vary at all from that price. Because like what good is a predictor that gives you the right price but can predict like, I don't know, plus minus $1 million from that price? Like that's not going to be very helpful. Or it's not as good as something that's more, okay, that's like where these terms are going to be used. And then turns out there's like multivariate versions of all this stuff. And the formulas become kind of confusing. This is going to be in the course notes. I'll share these lecture notes. They're online again. But the story is almost the same, except you always have to deal with this annoying case of like, if you have multiple random variables, one can be discrete, one can be continuous. If one's discrete and one's continuous, well, then you have to break them up into their corresponding integrals and sums. And so there's for two random variables, you have all these 4 cases. If you have more, there's going to be even more cases. It gets even more annoying. In this course, we're never going to have more. It's always going to be 2. But these will actually be important. And there'll probably be a question in the assignment using this thing. There's going to be an example below that I go over in the tutorial. But like the simple story you can see, for instance, is when both the random variables are discrete, the thing you do is as you would expect. And what I mean by that is the expected value of some multivariate random variable, and here it's like a function of it. If it's, this function is just only more general than what you saw. So like if you have the identity function, okay, actually just forget about that. Okay, so you have a function of the multivariate random variable. That function better produce a real number for you, right? Because you need to take the expected value of the function. So this function better map to reals, and then you take the expected value of that function. And so what that would mean is you take the function and you multiply it by the corresponding like PMF or PDF, the joint PMF or PDF. If they're different, then you have to break them up into like the conditional and the marginals. But yeah, this is going to be the moral of the story, is that the formula is almost the same. It's just the random variable times the PMF or PDF, and then you sum or integrate over things. Yeah, and we'll go over an example in more detail in the tutorial. It's also here. It's this example here, and this is exactly the case of doing the like wine. You're trying to predict what wine you have, kind of given this information about some chemical. And you could think of this as like a multivariate random variable, where X is the amount of chemical, Y is the wine. And then you might ask like, yeah, you might ask what's like the expected value I predict the right wine or something, and maybe it's 1/6 in this case, but yeah. So we go over this example in these notes. Okay, that's all I wanted to say about these things. So you can, as before, expected values, there's variances, and then you could do the same thing for these multivariate random variables. And the formulas look similar, just a little bit more like details there. Okay, and one last thing, which is that you can also do expected values over not just multivariate random variables, you can do it over conditional random variables. And what that would look like is, again, kind of as you would expect. You would write something like the expected value of this random variable, which is like maybe a function of your random variable, conditioned on something. And the formula is like as before. It's the function evaluated at all the values of y multiplied by the corresponding PMF or PDF. And here we use the conditional PMF for PDF. Okay, that's all that changes. I think that's it, yeah. So that's all I have to say about that. And the final thing is there are some useful properties that you will see a lot in probability course and stuff. And they just allow you to work with like sums and multiples of random variables and stuff a lot easier without needing to expand all the formulas. And in particular, if you have like two random variables, x and y, you have these properties that are kind of holding. So the expected value of the random variable multiplied by a constant is just the constant multiplying the random variable. That should kind of make sense. Like if you have a dice roll and you have the numbers 1, 2, 3, 4, 5, 6, and you just multiply all the numbers by 2, then your expected value should just be the original expected value multiplied by 2. So like before your expected value is 3.5, now what does it become? If you have not numbers 1 to 6, you now have numbers 2 to 12. Well, the expected value becomes 3.5 times 2, it's 7. Should make sense. Okay, that's the middle between 2 and 12. Similarly, if you have expected value of x plus y, well, you could just think of them as the expected value of x plus the expected value of y. This also becomes quite useful in cases. There is this formula here, which I'm not going to explain too much, but it will come up later, and then we'll talk about it. But this is like you can write expected value of any random variable as this double expected value thing. And yeah, this might be confusing now. We'll talk about it later. Yeah. And then there's properties about variance, which is that the variance of a constant times a random variable turns out to be that constant squared times the variance of the random variable. And just like super high level intuition, you remember the variance was just the expected value of some like function, and that function looked like x minus the expected value of x squared. So you're like squaring something. So that's where this like c squared comes from. If you write the formula explicitly of variance, this becomes obvious why this is the case. But yeah, like the variance is talking about like the squared variation. So that's why constants actually become squared. Okay. So it means that if you have the variance of some like whatever let's say the normal distribution, and then you multiplied all the values by 2, you actually end up having like that PDF plot varying 4 times more, 2 squared more. Okay, and finally, here's 2 more properties. There's important things that happen when x and y are independent. And that is that the expected value becomes the product of the expected values. Unsurprising, probably, because if you write out the expected value, there's like these PMFs inside. There's like this joint PMF. But if it's independent, then the joint PMF becomes the product of PMFs. And then you just see that this is just the product of the expectations. And then you can do a similar thing for the variance. The variance, but now it's for the sum. So if you have the sum of 2 random variables, you get the variance or something. This will be like on the formula sheet for like a midterm and stuff. And yeah, there'll be times where you get asked questions about like, you have one random variable, you have another random variable, you want to know what's the expected value of them being multiplied. Well, you use this kind of formula when there's, yeah. So just like thing to keep in mind, when you have random variables and there's like multiples of them or addition of them and things like this, and you get asked about the variance or expectation, first refer to these properties. You're almost always going to use these properties to get to something that looks like the sum or the multiples of simple expectations. Just like, and what I mean by simple is expectations or variances over single random variables. And then you apply those. And once we get more into the course details, we'll see why these become useful where. Here's a question. What is the difference between the 2 functions? I don't quite understand that, but this was 10 minutes ago, so I don't know what 2 functions they are talking about. Okay. So that is actually the end of the probability world. It gets a little more like, I guess, mathematically heavy when you get to the multivariate stuff, but hopefully if you know the like intuition from the single variate case, you can then reuse that and use the formulas for the multivariate case to like at least have some intuition of how things work. And once again, I'll try to go over these. There's some examples that I didn't go over. I'll hopefully have time to go over them in the tutorial. They'll be written up in more detail in the actual like course notes, not these lecture notes, but the course notes that are actually like a PDF file soon. And then hopefully there you can understand them better. Okay. At this point, is there any questions about this probability stuff? Because the next thing we're going to do is talk about supervised learning finally. Okay, so I was thinking about how to do these lectures. So what I did is I shared two versions of the notes. And this one has like parts that are not filled in. And I think those are the important parts. So I'll write those live during the class. And we'll see how that works. But I shared both. So there's one that has everything filled in, the other one that has parts blanked out that I'll write in class. I'll basically be writing exactly what's to be filled in. So yeah, we'll see how this goes. Okay. So supervised learning. So this was like the whole point of the class. I now argue that we've gotten most, and unfortunately not all, as you'll see, of the math tools required to understand what we're going to do with this, like how to solve this problem. And so now we talk about the problem. And we immediately notice we're already missing some crucial parts. Okay, so supervised learning was this idea of like learning from randomly sampled, which we just had this whole discussion about probability, about what randomly sampling data means. And before we used some math notation to denote what a batch is, and a batch was like this tuple, n-length tuple. And labels meant that we had these like XY pairs. Okay. So we talked about all this information about the data. So now we understood like, okay, what is the data that we have? Like, what does it look like? What is it randomly coming to us? And what does that mean? And things like this. But what we haven't talked at all about is what does learning mean? And in particular, like, what does learning well mean? Like, we had this whole intuition that like, you get this data, you have this thing called a learner, it takes in the data, produces a function. That function is called our predictor. But then like, what is a good predictor? We didn't talk at all about this. Maybe we had some intuition that like a good predictor means that if I see a new house, then I can predict its price correctly, right? Or maybe if like I see a new wine, meaning I see the amount of chemical in new wine, I can predict what wine it is. Or like for ChatGPT, if I see a new question, a new prompt, someone prompts me with something new that I haven't ever seen before, I can give them the right answer. It's kind of like the high level intuition of what we have of a good learner, or what learning well means. And we're going to formulate that in this I guess set of notes here. And more precisely, what this is going to be like asked, like what I'm asking here is like, what is the objective of learning? Okay, so how do we formulate this mathematically? What is this objective? Okay, that is the goal. And to understand this objective, we're going to just like write down a little, like, I guess we're going to write down what is our setting, like what is the things we have to start with first, and then we'll write the objective. Okay. And these are all the things that we've said before, and I'm just writing them all in one place here, which is that here is kind of like, and when I write setting, what I mean by this is like, this is a kind of like, it's called sometimes the problem setting, or like the assumptions you have, or like what you're starting with. So the thing we're starting with is a data set. So here's a setting. We're given a random data set of size n. This is how it would be usually like communicated in machine learning. You're given a data set of size n. The data set looks like this. It has n feature label pairs. Okay. Then you're told this information, which is that these feature label pairs are independently sampled from some common distribution. The same identical distribution. That's what I meant by common. Okay, so you're given this. Usually, like I'm just writing everything explicitly here. This thing, as I said, is called like this is sometimes called features. More precisely, we're going to call this a feature vector because it's actually a vector for this course. So we're given each one of these xi's and yi's is, so each xi is a feature vector. Each yi is called a label. So I've been using the word label throughout. I just want to point out this is sometimes also called the target. Okay? So sometimes I'll say target maybe, sometimes I'll say label. This is interchangeable as well in machine learning. So you have feature vectors, there's labels and targets. This is what it means to have labeled data. Okay. And so we're always going to assume the features are vectors. Oh. That's going to be just the assumption. So you can always think of it as being an like R2, R3, R4, depending on how many features you have. Okay. So we've roughly talked about all the stuff. I just want to give some explicit examples of what features and labels look like. Okay. So explicitly, we talked about the house case. So here, maybe if you have 3 features for each house, that would mean that your xi's are in R3. And the features might look something like the number of rooms, the number of floors, and the age of a house. Okay. So you would say each xi is in R3. Each dimension means like the corresponding thing. Yi is just the price. Okay. And it's a real number. Here's 2 more examples. So maybe your features are in 2 dimensions. And now you're talking about like this thing called classifying wines, or like predicting the type of wine. And here you might have the amount of chemical 1 in the wine bottle and chemical 2 in the wine. Then your corresponding labels are now the type of wine. And here you might sometimes use numbers to represent this. So maybe 0 means some other wine, and 1 means this like Barolo wine. So these are the two examples we've seen. I was going to write the version of what ChatGPT stuff looks like. It ends up being a little bit more complicated, so I didn't do it. But you can imagine there's some features. That features is like the text it gets as prompts, and then the label is the target is to predict the next word. But that's just a high level thing I'm saying in words. Okay. I didn't actually write it down. But here's like an actual thing that's also is like there's this really classic machine learning example of like predicting images, right? So what you do is you get a picture or like an image. And like, how do you represent this image? And so here, this is what I meant by we're always thinking of features as vectors. Or sorry, yeah, features as vectors. So everything in machine learning, the goal is to represent it as like a number, or like, sorry, like let's say this tuple of numbers. And the way we would do this for a picture is we would represent the pixel value of every single pixel in the image. So if it's like a 20 by 20 pixel image, which is not, that's a small image, right? Usually you have like a giant image, like what is it, 1080 by 1920. That's huge. That's like more than a million pixels. But here I've done the smaller case. Then you would represent this image as an element of r to the 400. It would be like this giant tuple of 400. Just the x vector would be this long thing of 400 values representing each pixel value. And then the corresponding label would be this. Is it, let's say the picture, you only had 3 kinds of pictures for some reason, which is cat, dog, or bird. And when we talked about this, like in the very first class, this becomes like important, let's say in like self-driving and stuff, because what's your image? Your image is like literally like frames of the street view you have. And then it's important for you to like understand what's a pedestrian, what's a light, what's all this. So you need to be able to classify everything in the picture. And there you might output like, oh, in the image I see a cat and a dog, or I see like a red line. So you have many more possible types of like classes here and so on. But this is like really how they represent these things. There's like they just write it as this giant thing. And the goal is to predict what's in the picture. Okay. And here's something I wanted to note that you might be thinking, it was mentioned maybe once or twice, which is like, it's actually not so clear cut what a feature and what a label is in a lot of these cases. And okay, let's just go over what I mean by that. It's like, maybe your features are like, you're given a number of rooms and you're given a number of floors, and you're asked to predict the age of the house. Like, that's also a valid problem. I could have said, why was the age of the house? So you might notice it's not like clear-cut kind of what are features, what are labels. And usually, this is like, it's really a design question of like, what do you care about? And usually the features are going to be, the feature is the info that's easy to gather about something. So maybe it's easy to gather photos or like images of like street things. You can just gather everyone's like Teslas, they have like all these images, you can get all that info. But what might be really hard to gather is someone that actually like the labels of everything in the image, right? So in this case, labels are usually the thing that's like hard information to get about some like object. And the features are usually the easy stuff. And so maybe in houses, it's hard to know like the price that this thing is going to sell for, or you don't know what it's going to sell for yet because it hasn't sold. But it's easy to gather like information about that house. But you can imagine other cases, maybe it's easy to gather the number of floors, the number of rooms, but it's hard to go like find in the files the age of this house because that's hidden in, I don't know, something like this. So yeah, totally depends on your problem setting. And it's totally your choice to like kind of design what is a feature, what is a label for the goal you have in mind. Okay. And there's a question here, which is how is X an element of R to the 400 to represent the pixel value of an image? Do you mean each pixel is the feature here? Yeah, so like, okay, so each image is represented as a number in a 400 dimensional space, right? So what that would mean is like this X tuple thing here. This thing would look like this giant like tuple, and since it's a vector, we write it as a transpose and stuff. But like it would have some value, maybe like 1, maybe that's the pixel value of the first image. And 400 more of these values are actually like 398 more. And then you have another pixel value, which maybe is like 70 or something, I don't know. Just tells you like the brightness. And actually in real life, there's like an RGB value. So each of these has 3 more, but for now, we just think maybe this tells you the brightness of the pixel. So like black and white images. And so, yeah, this is like, this tuple right here would represent an image. It would tell you the exact brightness level of every single pixel of the 400 pixels that make up the image. And this would be one like one feature in your like whole data set of feature label pairs. Let's say if you have a data set where n equals 100, what you would have is you would have 100 images, which means you would have 100 of these features and their corresponding labels. Okay. So what does our data set look like? Just like to remind, it's like the data set is going to actually contain the features, like let's say these images, and their correct labels, right? Well, you'd hope they're correct labels, but like we're gonna assume they're correct in some sense. It's like, and then their labels, Ys. And your goal is to then going to be like to learn something from this information, which is going to be, roughly speaking, and we're gonna formulate in a second, is like, given a new feature, can and I don't get the label, can I predict the label correctly? So now we write. Okay. And so like, yeah, this is actually a pretty good place I was hoping to get to, which is good. Okay. So we try to write the objective. This is like our goal, so we're going to try to do it. And we're going to slowly iterate on this. And it won't take that long, actually. So we start with what is, I would say, like an informal version of the objective. And this is kind of what our intuition tells us. And it's like partly formal, partly informal. And we'll see where. Okay. So here's the goal. The goal is to define a learner, right? We want to define some learner, like a learning algorithm or whatever. So define a learner. And we called this learner A, right? And I'm just going to write the whole thing explicitly. So we wanted to define a learner that takes in an input, which is a data set. And a data set comes from this set of all data sets. And it's going to map to some prediction function f. So that looks as follows. Okay. So we want to define a learner. But what do we want from this learner? Well, what we want is for it to like produce a predictor that's good. So let's just write that. So what I mean by that is that you want to define a learner such that the predictor, and we're always going to call this predictor that produces f, is good. Okay, and we're going to talk about what good means in a second. And where the learner with the input, the data set, is outputting the predictor f. Okay, so let's just read this one more time. Right? I want to define a learner, which is going to be a function that produces a predictor, such that when I pass in a data set into this learner, it's going to output a predictor f, and I want this predictor f to be good. Okay, so we haven't gotten maybe that far. This is kind of like what I've said. This is like the whole ambiguity was, what does this good thing mean? And so, okay, that's going to be kind of the goal to answer. But I made it a little more formal. So the question is, what is a good predictor? Okay, that is the question. And so, yeah, actually, we can do a couple more lines, and then we'll end the class there. So we'll have like a rough idea of what this good predictor means, and it's kind of like as you would expect. Okay, so we'll do this through an example. I thought is a good way to think about it. So you might have an example where you have some predictor, and so maybe your predictor takes as input some feature x. Okay, and so here I'm going to say this is a predictor that takes as input the number of rooms. So that's what x represents. And what is it going to output? It's going to output a price. Okay. So this should be reasonable. Takes in the number of rooms, outputs a price. Okay. And this is just like, so that's what the predictor does. So then here's the story. Like we suppose we're given, suppose we are given the number of rooms. So someone comes to us and like gives us a new number of rooms. Maybe we've seen it before, maybe we haven't, but it can be any number of rooms, in our data set or not. Like they give us a new number of rooms, and we'll call this is what this thing x represents. Okay. And notice how there's no subscript I. This is not like it is not necessarily in our data set, just some new number of rooms. Okay. A number of rooms x of a house. Cool. And the important thing is that this thing might not be in the data set. This is really important. It might be, it might not, but like we want to do well on any number of rooms we're given. And the important thing is we think about the fact where we are not given the corresponding label y. So let me write like this, given the price. So we're not told the price of the house, but we're given the number of rooms. Okay. And now we ask, okay, like, what would a good predictor f of d, oh, f of x do? Okay. And so, yeah, like as you would expect, the answer is going to be something like, what's the answer? It's like f of x should be equal to, or maybe like, you can't have that high hopes. It's approximately equal to y. Okay. So that's going to be like that's what we want. We want this predictor to be approximately equal to y. Ideally, it's exactly equal to y. Maybe we can't always achieve that. So, yeah, let me leave you with one sentence, which is like, this is the thing we're going to try to do next, which is we're going to want some like mathematical measure of how close a predictor is to y, so that we can pick what's a good predictor and what's not. And so the question remains of like, how do we measure how close f of x is to y? Okay. And so this is what we're going to get into next class, which is like, yeah, we're going to define what it means to measure how close this is. And then if we know how close a predictor is to the corresponding label, then we can finally like start designing learners that achieve this goal. And that's, yeah, that's the story. And the answer to the online question of where is the actual programming come and play? Yes, you're going to design the learner. That's the program.